started. So okay,
Okay, so let's just. All right. So
we'll
what is ARC?
okay. All right. Well, I'm gonna go back really quick. Let's do this in like 2 seconds because we spent a long time on this.
Yeah.
We've got two leaderboards here: the Kaggle leaderboard and the public leaderboard. Um, let's say really quickly what the difference is, and then we'll jump into what ARC is.
Sure. Yeah. So ARC is a benchmark IQ test. We'll get into that later. So there are two there are two benchmarks for ARC. There's the public benchmark and the private benchmark. The public benchmark lets you use the internet. So you can use large language models like Anthropic, OpenAI, you have to communicate with them through the internet. The private set is for local language models or any solution you come up with that doesn't use the internet. So you submit it on a Kaggle notebook that
Mm.
is divorced from the internet, and then it runs. And so for that competition, for the private competition, they have a special eval called the private eval because it never touches the internet, and hopefully it never will. And then for the public one, there's called a semi-private eval because it's possible that some of it might leak. It hasn't yet, to our knowledge, but so that's why you have the two leaderboards. And the private
In
leaderboard.
case you missed it, Jeremy's top on the public leaderboard. I mean,
Yeah.
we've been working on this ARC stuff for a while. Very exciting. Got 53.6 on the actual evaluation, 53.5 on the private set. So,
Yeah.
let's just say number one, at least on the release paper.
5.1,
5.1. You can see here the public eval. I guess you want to just explain to them why this is
Um,
different, like why this is not first.
Yeah, so public eval is you can go online right now to arc.com, maybe we could do that, and you can just download
ArcPrize.org.
ArcPrize, and you can download this eval, and this is basically what you train your model to do well on. And
Yeah.
so you can imagine that you can very easily overfit your model, that is, train it to memorize the answers on the public eval, or just train it in a way that it does, it doesn't quite generalize in the general sense, but it does well on these specific tasks that you've already trained it on.
Yeah, so here you can see it says they consider it overfit if there's a greater than 10% difference
Yeah.
between this score and the
And
eval score.
in a perfect world, the eval score and the semi-private eval, assuming they're of similar difficulty, you should get the same score on either one. And so, clearly I overfit wasn't intentional, or maybe it's a bit harder. I don't know.
Yeah. Okay, so I think the most interesting part of all this is like how it actually works. So first of all, this is the ARC Prize site. Here you can see the winners. It looks a little cooler. Here's the public high scores. Got Jeremy at the top. Then we've got MIT, Greenblatt, who Jeremy mentions a decent amount in his write up, which we're gonna get to in a second. Down here we got some picks. Here we are with Mike, Francois, Brian, and Greg in New York. Very exciting. Okay, so let's kind of get into the write-up. We're pulling this up on params.com. If you guys want to follow along with the write-up or see the website we're on, just go to params.com. We'll highlight a bit what that website is in a little bit. But for now, I'm going to just zoom in on this a little bit. And let's just go section by section really quick. We don't have to, I guess, read all of it. Maybe I'll even do a separate reaction video because it's pretty cool. But just give me like a quick breakdown of the strategy here with the evolutionary algorithm, what you saw in Greenblatt's and all that.
Yeah, so Ryan Greenblatt, I guess 6 months ago, got the state-of-the-art score of 43%, and that was like by far the state-of-the-art score. And he did it by basically asking GPT-4o to come up with tons of Python programs that will solve an ARC challenge. And then he actually has a revision step where he says, okay, let's try and revise the ones that look promising. And that also helped a lot. And then he submitted that. So, he might end up submitting like 1,000 Python programs that try and solve ARC. And maybe we could also just do a quick explainer on what ARC is exactly.
Yeah, I guess we glossed over. I mean, maybe I assume everyone watching knows what it is, but you know what? Let's just I guess I'll pull up the site and you can kind of describe what the test is like.
So basically, it's an IQ test for machines, and it's supposed to test general reasoning ability, or your ability to basically generalize from examples. And so the key is you're given an input grid, and then you're given an output grid. Here is a real example, right? And then your job, given the examples of input output, is to do a test input to output. So you're given the input, and then you solve the output. And so if you go back to where we were, you can tell that the answer is pretty easy, right? Just fill in dark blue.
Yeah, so you can see just so everyone kind of knows here. So like, here we have example 1, then example 2, and this is what you would ostensibly feed into your program.
Correct.
And then you tell it, hey, here's my input of the actual test case. give me the output. So if you get this correct, so obviously you can tell that you just want to complete the squares with the darker blue squares. So to a human, this seems pretty obvious.
Yeah.
But as you get a little bit harder, they start to. I mean, I guess if you're looking at this, you're probably going to think, oh, I could solve this in like a quick second.
Yeah, but that's also the key to ARC, which is smart humans actually can solve this quite quickly. So I think the average human gets around 85% on ARC. But again, you just ask GPT 4.0 just plainly to do it, it gets a 9%. So there's clearly something interesting going on, right? Where we think these machines are so smart and they do so well on benchmarks, but for simple reasoning tasks like this, they're actually quite stupid. And generally, they can't generalize. And one of the keys here is that you won't find a lot of the answers on the internet. And so they haven't had a chance to memorize the answers. And so, yeah, that's a quick explainer. And I guess I can then go into...
so here you can see it's all these sort of like visual pattern, recognition ones and stuff like that. And I feel like everyone has the instinct when they first see these to just feed in the... are we getting the feedback?
David just asked if we're screen sharing. I'm not sure if the screen is coming up.
Oh, fuck. All right. Well, I'm learning about... We're
All right. Well, that's also quite
okay. Take number 2 there is the...
Okay. Well, maybe we should just...
We are now screen sharing.
Can't screen share.
No. We're screen sharing now.
Oh, we are now.
Yeah.
Okay.
Our stream that we have here is delayed. So...
Oh, okay. We're screen sharing now. Okay. Well, damn. Okay. Well, let's just here some examples, right? 3 examples of input output, and then to the right we have an input, and then you just have to fill in the
simplest
output.
one.
Yeah.
Oh, you're on the first task. Okay. Yeah. Here's
so
second time going over this choice.
And so anyway, so what's surprising is this is supposed to be an easy thing to solve, right? For humans, it is a very easy thing to solve, but for large language models, it's difficult. They have a difficult time doing it. Again, the state-of-the-art frontier large language model 01, which is supposed to reason really well, which does reason really well, gets like a 19%. Again, humans get 85%. So the question is, can you organize code or a program such that you can get a really high score on this test? Because humans, our brains are good at it, but as of now, there's no machine that is good at doing it.
Yeah. Okay, so we kind of covered what ARC looks like, and again, it's like you see this and you're just like, oh, I'll just pass some screenshots to 01. It'll crush it. And then you go to the results and you just like, I guess this is the actual technical results, and you just hear, you can see 01 preview, when it raw dogs it, it's getting 18 to 21%, which is, I mean, it's it's much better than what it, it's a huge jump from 4.0, but super far off for something that seems, seemingly easy. But clearly, if Sonnet's getting 14% and then 21% on the other one, let's kind of break in now into the paper to see how we got,
sure,
how we're talking
yeah,
your score.
So okay, so the question is basically, can you coerce these large language models hard enough, get enough, hit them in certain ways with different prompts, and send so many that, is there
no, I think this is from 2 minutes ago,
that you can get them to actually solve some of these questions, right? Because we know that they have some knowledge inside of them, right? Can you knock that knowledge out to get them to actually solve one of these tasks? And so that's what I do. So the way I go about it, and this is inspired from Ryan Greenblatt's post, who got the state of the art before I did, is I generate a bunch of Python programs using Sonnet 3.5, which I find to be the best model. And then I take, let's say, the top 10 of those, I combine them together.
We're good.
Okay. I combine them together to create a new prompt, and an even better, combining the top 10. And then from those 10, I generate another 10, and maybe we can go to the visual.
Yeah. Okay, so I'm gonna kind of skip to this part because this is like what's really cool to actually see it. So here Jeremy's talking through his actual like, the methodology. I think we should actually look at the visuals and then loop back up to this.
Yeah. Okay.
Okay.
So here's an example of what.
Describe like what each color is.
Sure. So you start by generating 10 examples. So you call Claude Sonnet. You say, hey, give me 10 Python programs that might solve this.
And you feed it, the
you
ASCII
feed it the examples, and how you feed it is also interesting. That's in the next section. That's covered in prompting, so we can go into that later. But basically, imagine you have a really good prompt for how to solve this, right? And so you say, hey, generate 10 Python programs that will solve this. Okay. And then what this is saying is, okay, take the top 5 Python programs that you just generated, and we're going to discuss how to get the top 5. Like, what's the function to get, what does a good program mean, right? And then for each of those, generate 5 more programs, right? And then pool the top 3 of those, and then generate 10 more from those. Pool the top of 5 of those, create 5 new prompts, and pool and create 3 new calls to the large language model from those 5, and then ultimately take the best 2 and then return as your answer. So the idea is you can kind of see it like an evolution, right? Like it's like generations. So you have
Yeah.
generation 1, 2, 3, 4, and with each step you get closer and closer to the solution. And so actually one of the keys is how do you know whether a function is good or bad?
Hmm.
And the way you can do that is actually you can run the function. So the function is really just the rules of the transformation that Sonnet thinks is happening, right? So you can just run the function on the example programs. And if we can pull up maybe an
Yeah.
example, you can run it on the examples. And then if you go up, there's
Yeah.
so imagine you run the Python program on these, examples to the left. And then if you get a perfect accuracy, there's a good chance that the function you just ran is
Yeah.
actually a solution. Imagine you get 1 or 2 of them correct, then okay, it's pretty good, but it needs to be improved. And
Right.
that's the key. So basically what you're left with is a bunch of slightly incorrect functions that you keep on iterating on generation to generation to finally solve an ARC problem.
And so like one way you could do it, I guess, is if you just had like a single branch, you could just say like while incorrect, just keep on going every
Yeah.
single time. But like you could just have it, no breadth and just infinite depth there. But
Mhm.
I guess how did you decide,
Right.
what the initial breadth should be to, make
Yeah.
it 10 and something like that? So,
Yeah.
clearly we have kind of a config here. I'm hinting at what we're going to look at for the code
Yeah.
later.
So, and this is just an example config. This is not the architecture I actually use, which is below. This is just for an explanation.
Yeah.
So you can imagine, right? If you have it's kind of like human evolution, right? So if you have the same family members that are just generating generation after generation after generation, the odds that that one family survives are kind of low as a species, right? You want diversity in your species, and so you can imagine if you have like one function and then you improve it and improve it and improve it, it could be stuck in some valley with no hope of actually escaping to the correct solution, right? And the way these large language models work is they're heavily influenced by the prompt, right? So really what you want is a huge diversity of possible solutions, right?
Hmm.
Huge search space of possible solutions. And then for each one of the ones that are promising, you want to narrow down, narrow down, narrow down. And you also want to inject some genetic diversity into each of the generations, which is what I do in my pooling prompt, which we'll get into later.
Yeah.
So then the question of like how deep do you go versus how wide do you go? Because
Yeah.
of course we have finite resources. That was just vibes.
Right.
That was just like me, testing this.
That's what I was getting
Yeah,
towards.
for a
Yeah.
while.
Okay, so I think this like sort of tree-like structure makes sense. Obviously, the main idea and one side note I'm thinking like, is there like a chat somewhere? Because I don't know if people have questions, but if anyone knows where a chat is, just shoot it to me over DM. Otherwise,
I'll just say
um,
people have DM'd me.
yeah, I'm getting a
Okay.
few messages, but I'm trying to avoid looking. Okay, so uh obviously you're breaking at any point where it works, right? So this is
Yes,
just
that's
in
correct.
search of the solution. And if at any point you get a function such that when you test it on the 3 examples, if
Hmm.
it gives you the correct outputs for
Hmm.
each one of those examples, you're like, all right, boom, break, and return this
Correct.
here.
Yeah.
Okay, which will be relevant for the compute limits later, which we'll
Yes.
talk about in a little bit. Okay, so let's talk about the other sort of visual representation now, which is the search space, as
Hmm.
opposed to just viewing it as a
Yeah.
general tree.
So this is just for intuition's sake. I provided this graphic. So imagine that you have there's the whole canvas is this white part is the all of the possible Python solutions to a problem, right?
Yeah.
And then the green dots are the correct are Python programs that will solve the problem,
Hmm.
right? So obviously the space would be infinite and the green dots would be a very small percentage of that, but I'm just, we're simplifying it here. Okay. So that's the setup. And so the question is basically how do we guess a solution? How do we hone in on a solution that is inside the green dot? And so we do that if you go to the graphic by, okay, first let's just do a prompt and guess, right?
Hmm.
So here we have a uniform guess, right? Like we generate 200 guesses. These are the red dots. These are all Python solutions, right? And because we can run them against the examples, we can actually see which ones do well. And so let's just take the top 10, red dots that do great and then generate 10 more solutions for that. I think in this example, maybe it's select the, yeah, and then generate 5 solutions from there.
Mhm.
And so now you can see that we're actually the blue dots are generation 2, right? Like we're getting closer to the green dots. We're not there yet, but we're now honing in on some solution.
Mhm.
Then finally, we take the top blue dots, generate a whole new generation, generation 3 in black, and finally we actually have a solution, right? There's a black dot inside of a green dot, solution dot, which means, okay, we've got a solution. And that's the intuition behind what's actually happening here, which is you're basically using these large language models, which are glorified educated guessers, right? And you're using their glorified educating guessing abilities to hone in on the right answer. And I think this is where you know, the applications, not just, this is where this type of thing can apply, not just for ARC, right? Because if you view large language models as educated guessers, and it's your job as the programmer to like narrow them into the right thing to do. I think this is generally a decent approach to do it, especially for ARC. And I think, there are a lot of ways I know I can improve this.
Mhm.
And it worked really well.
Okay, so let's talk about kind of the overfitting local maxima type
Yeah.
problem that, if you just rank them by how successful they are, what the problem might be.
Sure. So you can imagine that you basically that you have a function that does really well at 2 of the 3 examples, right? And actually, you have 30 functions that do really well for the 2 out of 3 examples.
So I'll take this hypothetical from right
Sure.
here. 30 functions correctly solve example 1 and 2.
Yeah.
Only one function solves example
Right.
3. No function solves all 3.
So under a naive approach, or where you just have one parent, right? You might just take the top 10 parents, and then you would just run from there, right? But the problem is, it's actually likely that if it's just, if there's a solution path that is only solving 1 and 2
Hmm.
and not 3, it's actually quite likely that you're on the wrong path.
Mm.
You're in a local maxima, right? It looks like these are really good, promising solutions, but it's not, and you need that diversity of the ones that solve the right solution. So my idea for this was basically to create what I call a pooling prompt, which is injecting diversity into each prompt. So you take basically you have the parents are functions that solve various examples, right? So uh, every prompt contains functions that have solved every problem,
Hmm.
and that's called a pooling prompt. And it does really well, actually. The problem is the you can imagine it's more expensive because the prompts are larger,
Yeah.
and so you have to be careful with that because we're under compute constraints, and it also takes more time. So if you go down, actually, so what I ended up doing is, to get to a happy medium, I run pooling generations, and I run non-pooling generations in tandem, in parallel, and I found that this was what worked best. And again, pooling actually isn't always great,
Hmm.
because you can, again, you large language models lose focus when the context is too high,
Yeah.
right? So the good thing about having just 1 or 2 parents is that large language models can really focus and hone in on maybe a more correct solution, versus parents, it's kind of just getting knocked around a bit more.
And just like I know we're getting to prompting in a second, but when you're describing parents, what you're saying is basically you're adding to the string the prompt that you're giving it, saying here's
Yeah,
what previously went wrong, here's what previously went right, um, and just kind of expanding the context into the things that it has to attempt to reason about or remember through.
that's correct.
Yeah.
Yes.
So yeah, obviously as the depth gets larger, the context gets bigger. It's just more stuff for it to try to focus on. Um, I do want to talk about the pooling just really quick, in case anyone's kind of like confused about it. The description of the function that Jeremy's using every single time is basically just what what the Python program that it's returning, how successful it is. How are you counting how successful it was?
Sure. So two-pronged approach. The first is, how many examples did it get fully right?
Okay, so let's start from just like looking at the so you just generated a Python function, you ran it on the inputs here,
Yeah.
and now it gave you back 3 outputs.
Right.
Okay, so how do we assess how good it is? So first, just how many did
How
it
many
correct?
how many of the 3 examples in this case did it get? Let's say 2 out of the 3, right? Okay,
Okay.
that's the primary score. And then the secondary score is, how many total grid cell colors did it get correct?
Mm.
So just add up all of the grid cells it predicted, compare that to the ground truth
Hmm.
of what it expected, and then that's the secondary score.
Okay.
And the primary score trumps the secondary score.
Sure.
And so that's
Okay, so obviously you can see why originally at least that could end up with this local maximum problem where you could
exactly
guess one that oh, this function solved 2, that one solved 1, so the 2 is always better than 1.
right.
But yeah, okay, so let's I guess get into the pooling now.
Sure. Yeah, so that's the basic idea is basically you you know and this is all configurable, by the way, and maybe we can get into this
Yeah,
eventually
we'll
with
show
the
the
actual
code in a little
code.
bit.
I made it so that you basically construct a graph and well, in plain Python, and all of these variables that we're discussing, all of these things that we're discussing are variables, right? So how many parents for the pooling? 5, 6, 7, right? How diverse should the pooling be? What should the prompts be? Should it be using chain of thought prompts? Should it be using reasoning prompts, which are, maybe slightly different? All of those things are configurable.
Yeah.
And so, yeah. And this is actually um, one of the things I kept running into is, so I got a few $1,000s of credits from Anthropic. That's great. Thank you. And the problem is, just to run one challenge example on a full generation, if you go to that architecture, um, if you run it all through, that's 500 Python functions, large language model calls, and then that's also 31 different prompts, right?
Yeah.
So this is like $15, $10 to $15 to run.
Yeah.
So if I just did this willy-nilly with every change just to see, how accurate every change is,
Every console log
um,
costs $10.
yeah, no, it's like literally
Yeah.
but then to get a good sample size, like on prompt testing, I mean, this could be thousands of dollars, right?
Right.
Like hundreds of thousands of dollars. And actually, I think Ryan might have spent 40K doing this, and I spent a total of $2,000.
Mm.
So a lot of it was just kind of on vibes. I would test a few things. I would like very closely study the output and then just kind of guess and go on. um, so a lot of, these might seem arbitrary, and that's because they are arbitrary.
Yeah. Okay, so let me kind of continue down into this part right here. So yeah,
Yeah.
I guess as you're probably clearly about to get into, just compare this to a little bit to Greenblatt's, approach. Here you just have 200 generations, take the top two, get like that's I guess as shallow as it gets. Do you want to just describe this?
Yeah, so one experiment that I did do, because this is actually core to my thesis, and my thesis again is actually that depth is very important. So Greenblatt stopped at a generation of 2. I go to generation of 4, and I run multiple, like lines of genetics in
Can you
tandem.
explain just really quick exactly what he did in terms of his tree?
Yeah, I think it's actually just a simple 2-generation tree.
Okay,
So
but he generated, thousands at one level.
yeah, I think maybe because of compute constrictions, maybe it was like 1,000,
Okay,
maybe it's a bit
right.
less than that. Also, he was using GPT-4o, and OpenAI actually has this great feature where you can give it like a number of responses to a certain prompt
Yeah,
to return at the same time. I wish I could have used that. I didn't have any credits for OpenAI, so I couldn't really experiment with OpenAI that much, but
yeah.
it is a great model. Um,
We're frugal.
yeah, we're very frugal. A lot of prompt caching as well. That was huge.
Yeah.
Okay, so basically, I just wanted to see, all right, does depth actually help out, right? Like, if you run through a lot of generations, how much does it actually help? And so I did run this experiment where you have, and I'll just in plain English go through it. So you have just you generate 200 Python programs versus generating 50, taking the top 5, generating 10 from those, and doing the same thing over and over again. So they each generate 200 Python programs. They each generate 2,000 large language model calls, except the one to the right has 4 generations.
Hmm.
And so what I found is there's a massive increase. So there's an absolute 5% difference.
Yeah.
70% versus 75, which in ARC world is really, really big.
Yeah.
So clearly this is very valuable. And then I also, when I was analyzing it, a lot of the ones that the deep version got that the shallow one didn't were in the deeper parts of the net of the architecture. Specifically ones that have a lot of almost correct answers, right? Ones where 1 or 2 cells could be off. So in this
Hmm.
example, like sometimes they would get one of the blue cells would be red because it got tricked by something.
Yeah.
This is exactly what depth is for. Depth is for basically like meticulously, going through and just kind of honing in again, like to making sure until your accuracy is just 100%.
And it's worth
Uh,
mentioning, like on that point of like you're missing 1 or 2 cells, how important it is to be able to actually test this against the examples. So I feel like what the initial question, if you're just manually building software to solve ARC, is you just tell it, give me back the grid, right? Return a JSON of where the color should be, and that's it. The problem with that is how do you know if it's correct and how do you know how correct it is, right? So if you were just to go back to this original example, I assume that it would actually, you're generating these Python programs. We've discussed before that it would probably perform much better if instead of that, you just told it to give you back this grid.
yeah.
But the problem, of course, is you can't test it against the inputs.
Yeah. So actually what's interesting is, generating Python sucks, and it
Yeah.
introduces a whole new problem, which is now it has to generate the correct Python transform
And it has
function,
to keep
right?
remembering and has to like essentially interpret its previous, pattern
Yeah.
matching to understand that it did a good job to generate that code.
Yeah, exactly. So this sucks that you have to generate Python, but it's actually core to the solution, which is that you need a verifier. You need to be able to verify if you want to do this type of depth. That something is good, and if it just outputs grids, you just don't have a verifier.
Yeah.
And so, sure, your first layer will be more accurate, but then you won't be able to make it better iteratively. And this is actually why I'm quite optimistic about, like, I think large language models will continue to get very good at code because code is sandboxed, right? Like, it's not boundless in that you can always verify whether the code is correct because you can run it and run it against tests, versus maybe like how good it is at philosophy or politics, where you can't actually just verify whether the answers are correct or not. So I expect, like, for certain fields, large language models should get, significantly better over time. And then for certain fields, I would expect it to hit a wall because of this problem where you can't actually verify whether the solution is correct. And so reinforcement learning is very difficult. Like, how do you reinforcement learn a politics engine, right? Like, we can come up with ways, but like fundamentally, you're always going to have a better time reinforcement learning, you know, cursor.
Mm. Okay. So, let's continue on here. I guess this is sort of what we talked about, that there's a trade-off to how deep you can go. I assume you just stop getting returns eventually.
Yeah, as we can, all imagine, like, you make the depth too large and then you lack diversity in each level.
Yeah.
And again, diversity is very important. But what you want is diversity plus generation.
Okay, so the question everyone, everyone's gonna want to know what's the prompt. I'm always
Yeah,
I've been active lately on
sure.
Twitter saying like people should be open sourcing their prompts for everything. I'm tired of
Hmm.
this being like your secret sauce is like a
Yeah.
big string. Like just give me the prompts.
Okay, well, let's just
So
go to the appendix.
okay,
Appendix 2 has every single prompt.
all right. So what is the prompt that's actually
So,
winning this?
let's just start about
Okay,
that.
we can start at
Yeah.
two.
Okay,
Okay,
so the key to this is having a large language model do chain of thought reasoning, right? This is nothing new,
yeah.
tried and true, right? And so the first version has actually just straight up taken from Ryan's,
Hmm.
because again, like, every prompt update that you have to test is very expensive.
Yeah.
I wanted to experiment with less tried and true things, so I kind of just took this and ran with it. I did do a lot of edits. And just based on what I could tell, and as you can see, I also sometimes use a different prompt, which is below it, which is a more
And you can see here it's
descriptive.
telling it just to use reasoning tags, nothing
Yeah.
you wouldn't expect.
Also,
Chain of thought.
chain of thought is really just, hey, think step by step.
Yeah.
Ultimately, think step by step, explain your reasoning. This is important because then when you feed it back, back into the new prompt, recursively, it's able to, like, track what the former large language model said. It's nice for a lot of reasons, and for some philosophical reasons we'll discuss later.
Yeah.
Um,
Okay, so here's like the actual response that it gives
Yeah,
back.
so this is incredible, right? Like, this is what Claude responds. It's great.
So it
It's funny,
uses the
like, it's
reasoning
wrong.
tag. Yeah.
It's totally wrong, but it's awesome. Um,
It looks correct.
no, that's what's so funny about these machines, right? Like, they give beautiful responses that look extremely well reasoned, right? And it's totally wrong,
Yeah.
right? Like, oh, similar conversions from blue to red, the pattern continues, where it's like obviously doesn't continue,
Yeah.
right? So, these models are just guessing. They're not using deduction. They're not, they're constantly hallucinating. But that's part of why it's important to use, like, a lot of test time compute smartly, because,
Mm.
like, assume that that's going to happen, assume it's going to happen a lot, and then just have a good way to verify when it happens and weed it out. Kill the generations that are looking promising, and invest more compute in the ones that look better.
So I'm gonna show really quickly this example of what Claude responded. So obviously it gives its whole reasoning step, which you wanted to do first, and then it returns this Python program. Pretty incredible to see this. So again, it has to return a function called transform, which Jeremy's then gonna call in the examples, see how good they are, and then call in the real one. Just like look at this code. It's so funny how it would be so easy to just look at these and get it right away with your mind. But like
Yeah,
I
no,
would
I know.
never think to write this exact like, I would never think to write it this way,
Yeah,
It's
totally.
it's like we're making its job so much harder because we need to eval it.
Yeah, the verification problem is, like, I think, the problem
Yeah.
for large language models, which is, like, you need to be able to, when you're doing test time compute, whatever the output is, you need to be able to verify it. And unfortunately, in this case, that means we need it to formalize its thinking in a Python function.
I feel like we spend so much of our time, like, internally just discussing verification, like where this can, if we're going to be able to have a deductive machine, we don't need the verification isn't as much of a problem. And
Yeah.
so we'll get to that.
Also, maybe if the final thing we can discuss, and then we can be done with the prompting,
Sure.
is, and all of this you can just go on my write up.
Yeah.
If you go down lower, um, even lower, this is full system prompt if anyone's interested.
Look at how massive this prompt is.
Oh yeah, it's big. Okay,
Oh,
so
this
this
is
is
actually
just
really cool.
this is how
I love this part.
this is how I tell the large language model, like, this is how I represent the grids, right? So I don't just give it a Python list. And actually, a lot of this was inspired by Ryan's post, which was great. So if you go back, so I represent it through like a list of integers, but then I also give it a base 64 encoding. Can you go back to the, yeah. So I give it the shape, I give it an ASCII representation, just like this, super basic, nothing crazy. Again, mostly taken from Ryan, which was really nice because this would suck to have had to like prompt and spend so much money on this.
Yeah, my favorite one is actually the markdown representation of different colors given to it as opposed to just JSON. Like
Yeah.
I find it funny that this I wonder if it's just because it's fewer characters or something, but um that's probably the one that
This is also one, so you can actually, I tell it which colors changed as well. So
yeah.
this is just basically literally just what colors did change.
Yeah.
And then this is what a revision prompt looks like. So basically I will give it like numerous examples of like what I gave it and then what it outputted and then why that was not the correct output.
Yeah.
And as you can see here, yeah, so just more prompting, and then if you want to see what the pooling revision prompt looks like, you can just download. It's really big. It's massive, so it can't even
It's
fit.
massive. Yeah, if you drag it into VS Code or something, everything will get clogged for a second. But
Right.
okay, so I guess we've touched on prompting. We've discussed how the grid representation is provided to it. We have the different kinds of prompts. Is there anything else like on the actual implementation details before we get to, we should look at the code as well. I would like to actually show the code really quick.
Yeah, I can direct you to like.
Yeah, so just keep kind of this visual in mind as we look at the code because it really helps solidify the tree structure a lot better. So this is kind of cool to see. And then let's see, I'm gonna go back. So let's go to the files.
Okay, so go to source and then go to let's go to trees at the bottom.
Okay.
Okay, so then
I
let's
find
go
this to be
to
super
prod.
elegant. Yeah, it looks very nice.
So basically I have this idea where I want to express everything to make experiments really easy as just deterministic configs, right? And so you just, every config that you want to feed in, every architecture that you want to feed in, you just do that. I called it a tree. That was actually before I realized that you could have multiple but yeah, it's basically a tree. It's a graph, but it kind of looks like a tree.
Yeah.
And so yeah, go to prod. So we can look at the one that I actually submitted, right? So prod cackle tree. And so this is just
So I'm gonna
in
collapse
Python
these really
form.
quick.
This is just in Python form, like what I actually submitted. The graphic just shows this, right? So you start
Yeah.
with 50 examples, 50 Python programs. The reason you do 50 at first is because for some easy ones, 50 is enough to solve them. And you want to just solve them and move fast. Because again, you only have, so to solve the arc is basically you have to solve 500 challenges in 12 hours for under $10,000. So compute is a scarce resource.
Oh yeah, we haven't even discussed the compute
Yeah.
part very much.
So
this part was super
right.
interesting. The compute and the $10,000 limit. I guess let's finish up this like give me a quick like kind of rundown
Sure.
of this tree and then we'll
yeah, these are all the variables, right? So
Yeah.
how many in this node, right? In this node, how many attempts, what type of large language model, what the
Sure.
temperature. This is all about the prompting. Should I use examples in this one? ASCII representations, arrays, images, right?
So I'm gonna just go down because this is pretty cool. So you can see that like there's an actual just like this is the configuration for a root attempt, but then you can pass it fixes and it has an edge and you just keep going down and you keep passing these configs. It's all like on a class basis. It's very cool. And so you can just basically build out that tree diagram through this code.
Yeah.
And it just keeps getting deeper and deeper. What I thought was very cool about this is, if we had infinite money for testing, or infinite credits at the very least, you can just keep tweaking these, or you can even have it
Yeah.
generate trees for you and see which ones work the
Totally.
best.
Yeah.
It's just like a very elegant way of doing it. So I can, see here we have obviously these are the ones you experimented with.
Yeah. And this is all open
Um,
source, so you can just go and see it.
yeah, yeah. So this is I'm gonna link to all this. It's on Jeremy's Twitter as well. You guys should follow it. Gerber
Jeremy
888.
888. Made my first tweet today.
Yeah, his first tweet was winning arc. Very exciting. Um, okay, so then I would encourage people to read through this. It's pretty cool. So let's get back to the write up. All right, so obviously I'm spending all this time on this. This is literally it's a benchmark for the pursuit of AGI, or for at least detecting if our LLMs can generalize more specifically. So um, let's talk about
Sure.
deduction.
Yeah. So in doing this, you kind of naturally think a lot about how humans would solve our questions and then how large language models solve our questions. And I'm kind of left thinking that one of the main differences between humans and large language models is we literally use deduction. And by deduction, I mean, it's a premises follow from conclusions. An example is all humans are mortal, Socrates is human, therefore Socrates is mortal, right? That's a deductive claim. And when you make deductive claims, assuming your assumptions are correct, if your premises are correct, your conclusions have to be correct. And large language models clearly don't do this, right? They hallucinate all the time. 90% of responses contain like obviously factually incorrect information, right? They'll say this blue square should be turning orange when this yellow square turns green. And you look at it and it's totally incorrect,
Hmm.
right? And you have to wonder like why is this happening? And ultimately, it's because large language models are inductive machines. That is that they're trained on, next word, next token. And so with that, and induction is basically a guess from patterns that you've experienced, right? And of course, they're incredible. They're miraculous machines, and they have like, I think quite a nice world model inside of them, and they have high level representations of things. But fundamentally, their loss function is on next token prediction, and so they are guessing. They're doing very educated guesses, but they're just guessing. And I don't know, it's kind of my sense that you could solve ARC by doing something like what I'm doing, like making it better and then having a smarter base model
Mm.
that can make better and better guesses. Um, but it's unclear to me whether you'll be able to get generalized AI for things that are not unverifiable, right? Like, will you get an AI that can come up with special relativity? Um, it's not exact. I'm not exactly convinced that without deduction you can get there.
I mean, that one at least maybe you can't verify in the real world, but you can at least deduce your way to it, right? Because you can follow a certain theorem.
Right, exactly. But again, they're getting better all the time. I just have noticed kind of this fundamental flaw, and O1 is really, really good, but it still only gets a 20%.
Yeah.
So right there, you can see that it's PhD level memorization and guessing. Like it can have PhD level responses on things, but it can't solve ARC better than a 5-year-old can.
Yeah, the question I guess is if ARC is just where it has found the question is if ARC has found the one place where they don't care to train, or where they don't care to build the intelligence for it. That would probably be the best claim in favor of some sort of large language model, is that they're like, oh, we can make it to be good at this kind of task, but it doesn't have to. But of course, that's not generalizing.
Right. I think that's right. Then it's not AGI because that's not generalizing.
Yeah.
Um,
But the question still remains, like, can what you at least have concluded so far is this induction machine, like, can it eventually get to the point where it can generalize?
Right. So I could see two paths where I guess it becomes somewhat like AGI, right? The first path would be as it gets bigger and bigger and better, it becomes so good at mimicking human reasoning and deduction. And again, I think mimicking is actually a good word because that's kind of what it's doing, right? It's trained to mimic, text on the web. And so that's why chain of thought works really well, right? When you tell it to do chain of thought, it's mimicking chain of thought. But someone that mimics chain of thought, as in, mimics deduction, is going to be right more of the time than if they don't do that at all, right? Because deduction by happenstance,
Mm.
if you go through a deductive claim and it's correct, then it's going to be great. It's better to practice mimicking deduction than not doing that at all. Um, and so you can imagine a machine that's so good at this and does, test time compute so intelligently that it mimics this Einstein's level of deduction, right? And then at that point, that's pretty generalized.
Yeah.
um, and then there is, there's another way that this happens. Well, I guess we can basically there's another way this happens, which is uh test time compute is actually proxy for deduction,
Mm.
right? So instead of large language models getting so much bigger and better,
Yeah.
instead we can do this, like, let's say you do my approach, but you do it a billion times better, right?
Yeah.
Then it's possible that that is able to basically replace deduction. So I think those are
But
kind
that
of,
requires the verification step, right? Like you need
yeah,
to have some sort of if you do assume that's just going to become the best inductive machine ever, you do need some sort of verification. Like what ARC has that because we have inputs and outputs, and you can very easily kind of eval it. But
right.
for other more just reason-based tasks,
Yeah, I think that's generally correct.
yeah, at
This is
least
also a huge simplification. This is and the real answer is, very nuanced, I think.
yeah.
Um, so yeah, that was kind of what I was thinking in this section. And then it also led me to think, so I've been, getting really into, I don't know, just thinking about architectures, thinking about transformers. Um, and I was reading about an architecture Jan LeCun has been working on called Jepa at
Hmm.
Meta Fair. And I guess I was just thinking, like, how do we actually, if I'm correct, and or just generally, like, large language models, of course, would be better if they could actually use deduction, right? Like, if they don't hallucinate.
Hmm.
Well, humans again, like, but they're not using deduction. So if they could use deduction, they'd be great, right? They'd be much better. They'd be much more reliable. And so the question is, how do you actually get them to deduce? And I was just thinking, um, one main difference between humans and large language models is we think in concept space, and large language models, I would argue, think more in token space. And what that means is kind of when we think, I actually have in my head a high level representation of what I want to say to you, and then I put words to that.
Hmm.
And that's actually the opposite of next token prediction or
Right.
auto, where it's actually that they might have this high level representation, but at the end of the day, they're putting a word to it and then they're putting a next word, right? Um, Really, what should happen is they should have a high level representation. They should have a concept, and then they should map the concept down to words.
Mm.
And so it shouldn't be trained directly on words. You shouldn't be optimizing on next token because tokens are actually next words. You could come up with a million ways of saying the same thing.
Mm.
What you care about is the thing. So kind of like taking it a dimension above. And not to say that large language models aren't generating like profound, like understandings of words and concepts, but it's just that they're not optimized on that.
Yeah.
And so what Jepa's doing is this for images. So the idea is basically instead of predicting the next pixel of an image, and we don't have to go into, if we want, we can go a bit more into depth of how it works. But instead of predicting, the next pixel in image, what it does is it masks parts of images such that you learn to predict features, high level features of an image instead of the actual pixel. Because you can imagine, like, when we look out and we learn about the world through vision, it's not that we're like understanding the exact pixels of what we see, right?
Yeah.
It's actually that we just like understand the feature level of what we're seeing. And Jepa is a really clever way of being able to train on that. And so I was just thinking maybe we could apply the same thing to large language models. And I understand why there's skepticism at first, because like pixels are very different than tokens or words, because words, tokens have semantic meaning and they are a higher level abstraction than pixels.
Hmm.
But I still think they're still too low. What you really want to optimize around is the level above that, which is concepts. So you want to do gradient descent just directly on concepts.
Mm.
And I wonder actually if that is the key to developing deductive circuitry, which is basically if you are optimizing on the concept level, then it's possible that that is how deduction kind of arises. And I don't think, it's like, I guess, kind of a mystery to me why large language models haven't, and it doesn't seem like they ever will, like, produce deductive circuitry, because I think humans have learned deduction through induction, you know? And so,
But do you not like? Is there not some level of? I mean, again, maybe there's an obvious no to this, but is there not some level of deduction where like if when you prompt it, you're telling to go in one direction, and it then goes in that direction, right? So you say,
yeah.
"Oh, this is wrong," and it's like, "Oh, right, that was wrong." Now, sometimes obviously it just makes some shit up,
Mhm.
but other times it is taking, the reason that you've given it and applying it in some way.
Yes.
Your take would just be that it's able to, given every single word it's memorized, every concept, every book, every single thing that's kind of in the background, it's able to just assume the direction to go in.
Yes, that's
Yeah.
exactly right.
Okay.
Right, it's just saying, okay, if I were tested, like, how should I respond? Like how given all of the internet, like what's the best way to respond given all of the internet?
Hmm.
And that's different than thinking, okay, from the four premises that he just said, right? Like how do I conduct a conclusion? And generally those are the same because it turns out that to create a realistic sounding response, you actually do need to understand some concept of like what you're saying, but it's slightly off. And I think it's slightly off in the way that, deduction that they do is slightly off in that like there's something missing because it's mimicking. Like it is bound to hallucinate. It's bound to just come up with like less creative you know, responses, I would say. They're very good, but generally, yeah, I think it's clear that it's kind of like it's on the wrong dimension, I would say.
Yeah.
And it's kind of just a feeling you get when you talk to them sometimes, like you can tell it's not quite able to like really conceptualize and use reason about what you're saying.
Yeah. And at the very least, when it confidently gets things totally wrong, it really makes you feel that way.
Yeah.
But it's you're definitely left wondering, like, if the chain of thought were to be correct, like at what point would you be convinced that it's actually deducing? I guess if you can just give it premises and it gets from start to finish.
Well, I give the example in the write-up. I think if you train it on data from 1904, right, and below and before that, and then it comes up with special relativity from chain of thought. Again, this is before Einstein wrote about it, right? And it's not special relativity is not in the training data. Then I think we can call it AGI. Except, um, maybe that is the new Turing test. Like what I just said is just a Turing test, and it'll be obvious that large language models can do this in 2 years.
It's funny because, like, in principle, deduction is actually way easier
Yes.
because you don't need to invent things. You don't need to be creative. Obviously, the utility of this is very separate. Like the inductive machine, if we take your premise to be correct, is in many ways more useful, right? It could come up with all kinds of ideas and assist you with stuff like that. But deduction is just like an if then, right? So like if you're able to just represent all your premises as concepts
Yeah.
that always have to hold true, and you can always just as long as you can always conceptually verify them somehow, it doesn't sound like a harder architecture to actually achieve, right? Like in principle, I mean, maybe
Yeah.
on a technical sense it is, but um,
No, I agree. I think it's surprising that they are bad, that they can't. And like there's also a hypothesis that maybe, they have an incorrect world model, and so they would be able to do deduction if they had the correct world model.
mm,
But that might be a bit circular because like having the correct world model would mean they fully understand deduction, can use it. But I actually think it's more fundamental. I think that until the language models are optimized on concepts, and once you're optimized on the concept level, right, and not the token level, and that means again like what you care about is the whether the output is coherently correct based on the concepts, not based on the next tokens. It's not enough to sound good.
mm.
It has to be good, right? And that's the optimizer. Um, I think then I think deduction we just need to train it on the level above. And then concepts will lock in will figure itself out. And that's just a total hypothesis. Obviously who the hell knows. That's just what I was thinking when I was writing this.
Yeah, yeah. I
Um,
mean, it feels natural too. Okay, well, I'm gonna also share this website that we've been working on. So, in order to share this and some of the other ARC projects and related machine learning projects, we built this website called params.com. So you can go ahead and open params.com if you want to, and here you can see the code for the architects who actually got first place on the private data set and just 0.1% below Jeremy in the overall scoring, but technically they're doing it without using internet. So uh, in terms of who actually was on the paper, that would be the state of the art, at least on the paper. Because they got the official winning prize here. So if you wanted to see the code and even talk to the creators of Architects, you could go on params.com, find their repo here, click into it, and you can actually just book a call with them. So you can hit book a call, go through the sign up flow. I guess I'll do this a little bit later, but if you sign up there, you can see basically it's kind of like intro, but for engineers. And we're starting with these machine learning templates. It's all invite only. So if you want to submit your repo and become someone who can get booked for a call and make some money from it, you can send a DM to @params Inc. on Twitter. But if you go to params.com, you can book a call with the architects or here with Jeremy. So here is his ARC-AGI one. You can hit view repo and view this entire write-up that we were just talking about. You can also see the code files if you click here, or you can go ahead and fork it or open it on GitHub directly. Let me go back. And if you want to book a call with Jeremy, you can actually just go to this website, hit book a call, and you can pick how long the call is going to be, see his pricing, and just get right on a Google Meet in no time. So hopefully this was useful. I don't know if I have any questions in the chat. I don't think so, but mine has not been updating. So if you guys have any questions, just shoot us a message on Twitter. Is there anything else that we're missing here that we should have touched on? I'm trying to
I
remember.
think that's about it.
Let's see, we've got every bit of this write-up I think has been touched on.
Yeah, I'd say DM me or, book a call.
Yeah. And then also you can see Jeremy's churn prediction model in here.
Yeah.
Okay, great. So I'm gonna go ahead and cut this off. I don't know how we started out with no sound when I switched to the I think to the screen sharing one or to the non-screen sharing one. And then what was happening after that? There was I don't know. We've had a lot of technical difficulties, but it's all getting wrapped up now.
All
So
right,
let's end this off. And 200 people listening. I'm surprised.
wow, we're famous.
Thank you all for tuning in, and definitely send us any questions or hot takes about. I mean, maybe people disagree about the deduction.
I have thick skin.
You can take it.
And these are not strongly held beliefs, I would say. I'm always changing my mind on this, so.
Yeah, that's true. Okay,
Cool.
cool.
See ya. Okay.